Okay. So, this is our group presentation for biostats, and we are going to be discussing this case of a woman who is diagnosed with breast cancer in a community that has a known prevalence of breast cancer for 1 in 1,000 women. And we want to know what are the chances of having the disease in reality if she tests positive based on mammography. Now, in order to do this, we utilize the fact that the prevalence is 1 in 1,000 or 0.001. But it's difficult to work with such a small number. So in order to generate a contingency table, we can take, instead of 1 in 1,000, we say 100 in 100,000, so that we get a fixed number of total whole numbers of people. And then in order to fill in this table, we utilize the known sensitivity of 92% and specificity of 95% that are previously recorded for mammography testing.
Okay, so to fill in the table, since the prevalence is 1 in 100,000, that's the same thing as 100 in 100,000 people. And since the sensitivity is 92%, 92% of 100 will be 92, which would be the true positive, and then the false negative would be 92 minus 100, right? So that is the left side of our column with 92 on top and 8 below. To fill in the right side of the column, we use the specificity where we got, so for the total people who have the disease, we minus 100 from 100,000 and we got 99,900. We multiply 95% by 99,900 to get 94,905 as the true negative. And then to get the false positive, we minus the 94,905 from the 99,900 to get 4,995. And then we just calculate it.
Okay. And for the right side column, to get total of 5,087, we just added the true positive and the false positive, and we just added 92 plus 4,995, and then for the second column, the total of 94,913, we added the second column, so 8 plus 94,905. And now that the table is filled out, we want to know what are the chances of having breast cancer if the test was positive, which is the same thing as positive predictive value. And we know that equation for that is true positive over true positive plus false positive. So based on the table, we can calculate that. So that's 92 over 5,087, which equals 0.018 or also 1.8%.
Okay, so an additional way that we could solve the problem is using Bayes' theorem for rare diseases and probability. So in this circumstance, we want to find the probability of A that's contingent upon B, where we define A as the patient testing positive for breast cancer, and A is the patient actually having breast cancer, and we define B as the patient testing positive on mammography for breast cancer. So the chance of having disease equals the rate of the disease, which in this population is 1 in 1,000 or 0.001 times the sensitivity of the mammography test, which in our case is 92% or 0.92. For the denominator, we repeat the first half of the denominator, we repeat the numerator, and then we add it to the rate of not having the disease, which in the general population is 0.999 times the rate of the false positives, which is 1 minus the specificity of the test, which in this case is 95% or 0.95. And this gives us a chance of having disease is 1.8%.